Good morning, everyone. My name is Paula Vindigni. I'm a telecommunications engineer working in collaboration with the Bolivarian Agency for Space Activities on this project for the design and implementation of a nano and pico satellite tracking and monitoring ground station, which is their first approach for the development of a space mission based on the CubeSat standard.
The ground station is a fundamental subsystem in the development of a space mission. Its main objective is to maintain a reliable communication link with the satellite when there's a line of sight. So within that time window, it is possible to download telemetry data, send commands, and receive data from the payload. There are two ways to implement a ground station: with radio hardware or by the use of software-defined radio technology. The main drawback with the first option is the cost of the equipment and poor compatibility with open source tools, as they are designed to be used with specific applications. The software-defined radio offers the same results with a much lower implementation cost and compatibility with different software. Taking into account the resources we had available, we opted for the software-defined radio technology in order to achieve our goals for this project. The ground station is made up of four fundamental elements: the antennas, which, depending on the working frequencies, can be of different types and dimensions; the positioner, that's a rotor that automatically points the antenna to the satellite position and direction through a tracking software that provides azimuth and elevation coordinates. The positioner includes an analog controller for elevation and azimuth, and an external control interface for the rotor that works through a satellite tracking software. The radio frequency transmission and reception equipment sends the information to a carrier signal that is responsible for modulating it in the operating frequency of the satellite link. And finally, the computer, responsible for monitoring, control of satellite tracking, and storing mission data through a graphical user interface. We'll be working with the ATOS Research Universal Software Radio Peripheral B210, or USRP B210, designed to work in conjunction with an external processor and allows the realization of radio software. And for signal processing software, we employed GNU Radio Companion, which is a free and open development tool that provides signal processing blocks to implement software-defined radio systems. To get a better understanding of the equipment we'd be using to develop the project, we made a preliminary test creating a small ground station for NOAA meteorological data reception, motivated to the simplicity of the manufacture of the antenna that would receive data from the NOAA meteorological satellites. Here you can see the diagram of the NOAA meteorological image reception station. The first stage includes a 137 MHz turnstile antenna. The second stage, the USRP B210 radio frequency device, and finally a laptop for storage and decoding. The turnstile antenna was selected because of its optimal performance in receiving the signal in APT, automatic picture transmission format, from the NOAA satellites, and also for its simplicity and ease of construction. The data reception software. Here you can see the reception scheme in the GNU Radio Companion, where each block fulfills a specific function. The UHD USRP source is responsible for the communication between the GNU Radio Companion application and the USRP B210 module that is connected to the personal computer. A low-pass filter that suppresses unnecessary frequencies. The WBFM receive. It's a quadrature FM demodulator that allows the demodulation of the FM modulated signal on APT format transmitted by the NOAA satellites, and thus obtaining the AM modulated signal. Durational resampler. It's a block that will allow the resampling of the AM signal, obtaining a sampling rate required by the WX2Image software to be able to decode. The multiply const. The function of this block is to control the volume of the audio. The WAV file sync is an audio sync which will allow to store the AM signal in an audio file, whose extension is .wav. This stored audio file will be later decoded as an APT signal. Here we can see the image received from the Nanosatellite. The power level of the acquired APT signal is very low, which did not allow the WX2Image software to decode the images that were taken from the satellite. For the automatic nanosatellite tracking, the Yaesu G5500 rotor and its analog controller need an external control interface that acts as an interpreter of the data received by the satellite tracking software to send as voltage signals to the rotor controller. The manufacturer interface acts as a digital analog data converter. The rotor works with control voltage levels from 0 to 5 volts, which translates to 0 to 180 degrees in elevation and 0 to 450 degrees in azimuth. This data is sent to the controller, which interprets them and transforms them into voltage levels to place the rotor in the desired position. Here you can see the schematic of the external control interface, showing the needed electronic components for the design of the control interface, which were subsequently implemented for the manufacturing. For the satellite tracking and rotor control, we employed SimpleSat Lookdown, a free satellite tracking software created by Tom Doyle, which allows the following functions: to download satellite data from the software interface using the Celestrat database for satellite tracking, to configure the location of the ground station, displays a list of satellites added from the database to the software, creates a group to add preferred satellites, has satellite path prediction, rotor control options, and displays the satellites on orbital map and world map. Here you can see the connection diagram from the rotor. It is planned to use 2 cross-jagging antennas for the transmission and reception of nanosatellite signals in the VHF and UHF frequency bands. As we know, the cross-jagging antenna is a combination of 2 jagging antennas of identical dimensions shifted 90 degrees between them, sharing a common support. That is, the one is placed vertically and one is placed horizontally. Taking the central frequency of each band, which is 145 MHz in the VHF and the 436.5 MHz in the UHF frequency band, we obtained the length of the elements and the separation that should exist between them through theoretical calculations, showing the results that you see here, which were introduced in the 4-NEC2 antenna simulation program, resulting in the 2 cross-jagging antennas structured shown in the images. This simulation program allows us to visualize data of interest such as the 3D radiation pattern and gain and reflection coefficient graphs, and also offers an optimization tool that allows the variation of the values entered to obtain the best possible result of our design. In conclusion, it was possible to implement a configuration that allowed the processing of the APT signals from Nanosatellites 15, 18, and 19 using an USRP B210 radio, and the GNU Radio Companion Processing Block open source software. Having completed successfully the manufacturing of the turnstile antenna that allowed the Nanosatellites APT signal to be acquired. However, the signal strength was too low to be able to decode the frame. The manufactured low-cost interface allowed the Yaesu G5500 antenna rotor to operate perfectly in conjunction with the orbit prediction satellite tracking software. And with the use of software, we obtained the most optimal design of the cross-Yagi antennas operating in the VHF and UHF frequency bands. Currently, in order to continue the project, it is expected to start manufacturing these antennas and then start the first tests to receive data from the nanosatellites. Thank you very much.